This is the experiment to work out reaction mechanics. Thank you to Jeffrey Neuse for giving us this one. And the risk assessment generally says everything else is fine, but the actual product is not. So you need to keep that, and risk assess doesn't cover that. It's nicely done here, so you know which mils to add. So the propanone, iodine, sulfuric acid, and the concentrations are given to us already. And so what we're going to do here, it's just very quick to set it up in burettes. So the students just very quickly add the correct number of mils of propanone in one test tube, and then to a separate test tube they add the potassium iodide here, and then the sulfuric acid and the water possibly. And then what we do here is we add the two together and then start the reaction. To mix them, you just give them a really good flick like that. And this one happens to be the longest one. So I might actually let this one run in the background, and it runs for a good 10 minutes, unfortunately. And so you can just sit there and see that eventually go clear. And so this is the data that we get. And what we did is we just processed. So we're going to look at the effect of H+, then iodine, then propanone. And so if you have a look at the H+, you've got to keep all the rest the same. And so the only thing that can change is the H+ concentration. And so you can see here the H+ concentration is doubled, and the rate is ×3. And so that's closer to a first order, which is concentration doubled, rate doubled, not concentration doubled, rate ×4. And so we're going to leave that as maybe it's a first order. If you take the hydrogen ion concentration and times it by 3, the rate is times by 3. So that one confirmed it is a first order. So obviously we could improve this a little bit by doing some repeats. For iodine, what we get is we keep the propanone the same, the H+ the same. So when we halve the iodine, what we're getting is the rate is ×3. And 4 times less iodine, the rate is ×6. So it looks like sort of a negative first order. And these don't have to be integers. They can actually be 1.5s and 1.6 negatives. And so this one looks like an inhibitor. Very strange. We'll go to the published results in a second. And then the propanone, you keep everything else the same. So you double it or triple it, and you're getting the rate double. And the rate close to a triple, so it looks like a first order. And so that one's fine. So just checking the data because I didn't expect it. This one's expected to be 0 order, and we're getting an inhibition, a -1 order. So a colleague's data did a much better job because they graphed it. So you can see it'd be even better to do a range of 5 to repeat it. And so they're getting concentration versus rate, so first order for the other two. They didn't call that as 0. It should be a flat line, but it is the same results. They are getting -1 as well. So just going to the published results. So just going to the ChatGPT. Can't trust it. I did get first order. It says it's 0 order. And it's actually -1, so it's an inhibitor. So I did ask it if it could come up with some ideas about how the iodine is interacting with it. So you can see that the iodine perhaps is forming I3 and slowing down the effect of I2. And so the problem with this is you actually need to do organic chemistry first. So you sort of need to know with SN1 and S2 reactions when we teach it to you how a carbocation is actually quite slow to form. You might know the saturation test adding bromine to a double bond. So this is very similar. Iodine to a double bond is quite fast and makes it go clear. And then just positive subtract a negative helps the reaction go quite fast. So is this true? It does match your organic chemistry reactions that you know about, and it does agree with the fact that iodine is not meant to take anything that's slow is the rate determining step. So the fact that it's this and this, this and this in equal proportions, a both first order is the slow rate determining step, and then everything else is quite quick, and so nothing else really matters. It also does make a little bit more sense in that an excess of iodine might be forming I3 with the I2, and therefore preventing this and this from acting. And so it could actually be an inhibitor. That experimental results are showing it's a -1 rate order, which I've never seen before, but that's what the data is showing. All right, and there is a proposed mechanism for it. So unfortunately, you guessing the mechanisms is quite a head spin, but at least once you've done organic chemistry, you'll understand where those proposed mechanisms might have come from, especially when you talk about rate, how those the electrons move, when you learn rate mechanisms for all of these. And also, at the moment, you should at least appreciate that makes sense as far as that being the slow rate determining step. Therefore, the I2 certainly not being a 1, perhaps a 0, and most likely a -1. Okay, so a little bit of a difficult one, that one.